Hi everybody. For the next couple of days, the lesson is going to be on centripetal force, but we're going to break it up into several different mini lessons just to make it a little bit shorter and a little bit easier to understand. Please print off these pages first before you start watching this. We're going to fill these out together. So have these ready to go. The first thing we're going to do is we're going to derive the formulas for centripetal force. Now the formulas that you were using on the work previous, those formulas were for centripetal acceleration. This isn't much of a derivation. In fact, it's probably the easiest derivation out of the entire year. You can see I wrote right here, recall that Newton's second law tells us F equals ma. Well, you already have three formulas for A, for centripetal acceleration. So literally, to derive the three formulas for centripetal force, all you need to do is sub in the result you already have for A into ma. So the first formula will be F equals ma. The first acceleration formula we had was v squared divided by r. That's formula number one. Second formula, F equals ma. But for A, we'll use the other centripetal force formula we were using. Sorry, centripetal acceleration formula we were using. 4 pi squared r divided by t squared. That'll be your third force formula. Your second force formula, sorry. And your third force formula will be the other one, F equals ma. And we had one other acceleration formula, 4 pi squared r f squared. So these are the three centripetal force formulas that we're going to be using over the next couple of days. Today we're only going to do one particular case, and it's probably only going to use formula number one, but let's see how things go. Now, the weird thing about these formulas is very seldom are you ever just going to pick one of these formulas and substitute values into it and get an answer. The questions are a little bit different than that. They involve equating forces together or using more than one force in one question. Now, if you remember from grade 11, every time we used capital F, we put a different variable in the lower right-hand corner just to sort of identify what type of force it was. So doing the same thing, you'll usually see centripetal force formulas written with a capital C in the lower right-hand corner, just to make sure that you remind yourself that it's a centripetal force formula and not friction or normal force or some of the other forces that we'll use. So the first type of question that we're going to do, and the only type of question that we're going to do today, are questions involving vertical loops. And the most common example is a vertical loop like you see in the picture here. What if you had a mass going around a loop and you wanted conditions to be right so that it didn't fall off as it was going through the loop? So I'm going to draw a circular loop here just to explain. So at any point during this question, when a skateboarder, say, is going around the inside of a loop, at any point during the question, let's say the skateboarder is right here. At any position during the question, there are going to be two forces on this object. There's always going to be a force of gravity, straight down. And because it's moving in a circle, there's always going to be a centripetal force that is straight outwards from the center of the circle. Now, at any position around the loop, that's going to happen. Gravity straight down, centripetal force straight out. So there's two key positions that always end up being in questions. Right at the very, very bottom and right at the very, very top. Because if you use the same sort of theory at those two positions, at the very bottom of the circle, gravity is straight down and centripetal force is straight out from the middle of the circle. At that position, both of those forces are acting in the same direction. So you get your strongest force. This is right at the bottom of the loop. That's where you find your maximum force. So if you were, say, a skateboarder, like in this question, going around a loop, at the very bottom of the loop, that's where you're going to be sort of pushed into the the inside of the loop the hardest. Now, if you go up to the top, though, at the 12 o'clock position and apply the same sort of idea, gravity's always straight down, but centripetal force is always outwards from the center of the circle. Well, at the very top, outwards means directly up. So here you've got a situation where the two forces are exactly opposite one another. In other words, the centripetal force, every newton of centripetal force is going to subtract away from gravitational force down. And this is where you have your minimum net force. So these are two important positions. The sort of what's referred to as the 12 o'clock position at the very top and the 6 o'clock position at the very bottom. All right, this looks like a bit of a mess. But if you read the question again, so this question says, if you have a 70 kilogram mass that's going around a loop, what's the smallest, what's the minimum required speed that you would need to have so that you could get all the way around the loop without worrying about falling off? So the key part to this question is at the 12 o'clock position. This is where you have your minimum force. This is where you really have to worry that you have enough speed to make it around this loop. If you don't have enough speed when you're at the 12 o'clock position, if the gravitational force is stronger than the centripetal force because you don't have enough speed, you will accelerate in the direction of the unbalanced force, which means you will fall. So what we have in this question is a situation like this. I'm going to draw it one more time. We have a loop. We want to look at the 12 o'clock position. And at that position, the force of gravity down and the centripetal force up, at the absolute minimum, you want these to cancel out. You want to have just enough speed so that the gravitational force is overcome. And hopefully you'll have more speed. If you have more speed, you'll have a greater centripetal force up, and that would actually press you into the inside of the track. But what if you had the absolute minimum? In other words, what if the centripetal force was exactly equal to the force of gravity and not greater than? We tend not to use greater than or less than signs in physics. It's always equal signs. So what you have on these centripetal force questions is you hardly ever solve for a centripetal force. Usually you're equating forces and trying to get an answer using a centripetal force formula. So we want our centripetal force to equal the force of gravity. And that would be the absolute bare minimum. So you look on your formula sheet for your 3 centripetal force formulas, and you pick the formula that matches whatever is in the particular question. This question today is talking about speeds. So our centripetal force formula that's going to be useful is mv squared divided by r. The gravitational formula, you don't have to worry about universal gravitation. This is just a question here on Earth. We'll use the old easy grade 11 example for force of gravity, mg. So, although 70 kilograms was given in the question, and you could use it if you wanted to actually call the mass Tony Hawk, the conditions here will be the same for any mass because there's a mass on the left and a mass on the right, and they're the same. So those cancel out. And the question doesn't even change for what skateboarder might be going around this loop. Now, what was the question asking? It was asking for the minimum speed. So we need to solve for v. And if you isolate for v, v is going to equal, bring the r over, it's going to be gr, and then this was v squared, so you'll also take the root of the right-hand side. And this isn't a formula that you should remember. This is just a rearrangement of the equation of these two forces. And different questions that you do have different ways of doing them, different formulas you might equate, different force formulas, and you might even be solving for other variables. So don't ever memorize formulas like this. Just start here. Start with the idea that you're equating two forces together because it makes sense why the centripetal force is going to be equal to the force of gravity. And then usually the answers to these questions are quite simple because the math actually isn't very involved once you get to it. G is 9.8 meters per second squared. And surprisingly, all that matters in this question is the radius. and it said the loop is 6 meters in diameter. Be careful, this is radius. So we're going to use 3 meters, not 6 meters. And then the answer to this question, and make sure you square root it, 9.8 times 3, take the square root. The answer to this question is 5.42 meters per second. So that means that you have to be traveling at least 5.42 meters per second to get around this loop without falling off. If you were to go slower, let's say 5 meters a second, the centripetal force up would not be as strong as the gravitational force down, and you would end up falling off the track. There are some practice questions today, and I'm only going to go through this one example, and I know it seems very short. There's only 3 questions, and they all deal with vertical loops like this. Now, some of the questions deal with the maximum force at the bottom. I think questions 1 and 3 deal with maximum force at the bottom. Question 2 deals with force at the top, but it's a little bit different in this example, and I'll let you try and figure out why when you do the question. So please remember, you can ask any questions you want, but do it on Google Classroom. Don't ask questions anywhere else. Don't ask questions in the comment section on this video, because I probably won't even see them. Let's all stick together on Google Classroom, and we're just going to use YouTube as video links to go off to for the lessons. I'll be posting solutions to the 3 questions a little later on, but let's start off slow as usual, and we'll focus on 3 homework questions only for today.